Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, are you wearing a robot? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we'll be finding out more about the incredible field of soft robotics and how it's being applied to develop wearable tech for use in medicine and rehabilitation. Before we get started, I'd like to remind you that you can send in your questions for my future guests, either by contacting us on social media. We're at Robot Talk Pod on all the socials, or you can submit questions via our website by going to robottalk.org. And don't forget to enter our competition for a chance to win your very own Robot Talk t-shirt. All you have to do is share your favourite episode on social media and tag us at Robot Talk Pod. So, without further ado, let's get on with this week's interview. I recently had a great discussion with Kris Dorsey from Northeastern University, all about wearable soft robots, healthcare, and rehabilitation. Today I'm speaking to Kris Dorsey, an associate professor at Northeastern University, researching soft robots and wearable sensors for medical and rehabilitation devices. Hi Kris, welcome to Robot Talk.
Hi, thank you.
So first of all, can you give us a little bit of an overview of how soft robotics and e-textiles can be applied to medicine and rehabilitation?
I think soft robotics and e-textiles can be applied in a lot of different places. So we have lots of fantastic medical devices, things like braces or bandages, where we want to measure a specific thing about a person and take an action. And usually that action is right now a chemical action, or we rely on the person themselves to, for example, change a bandage or adjust their brace. And soft robotics and e-textiles just looks like having a closed loop response to that, where the device, the robot, can take that action for the person.
Okay, yeah, that's really interesting. So, like in the example you gave of a bandage, how would it change the bandage in response to the need?
Good question. So maybe I'm thinking, I guess, less a bandage and perhaps more something like a tourniquet, or where you need to provide a specific amount of compression. And so maybe the robot senses, okay, that's a little too compressive. I need to loosen a little bit, or I need to tighten a little bit due to the person's motion. So adjusting the shape and size of the bandage or the brace, rather than, for example, switching out for a different bandage.
Sure. Okay, that makes sense. That's really cool. And yeah, the mind starts to go off in all kinds of directions about what you could do with this sort of technology.
Yeah. One of the things I love to do in my lab is just spend a couple of minutes playing around with ideas with my students. We get some really fun stuff coming out of that.
Yeah, I bet. So you lead the PASSES research group, which stands for Programmable and Reconfigurable Soft Engineered Systems. So can you tell me a bit about what you and your group are working on at the moment?
Yeah, so our goal with programmable and reconfigurable soft engineered systems is to make soft robots that are not always soft, but sometimes soft, sometimes more mechanically stiff or rigid. Sometimes they take different shapes. We are really interested in healthcare applications, so things like smart compression for people that need different compressive devices, but also how that gets used in soft robotics for things like grasping and continuum arms and being able to pick up delicate objects. So all the things that we think about that soft robotics are really traditionally good at, we want to think about how do we bring in all of the really great properties of soft robotics, but fuse them with more rigid or sometimes rigid robots that can give us the properties we need to pick up, for example, a really heavy object too.
So how do you change how rigid a soft robotic device is?
So there are a bunch of different really exciting approaches. One of them that we use in our lab is robots that are shaped like origami patterns.
Mm.
And based on the shape of the origami pattern, you get a different stiffness. So we can make a robot that's really compliant, and then we remove some air from the robot, and then it becomes a little bit stiffer just due to the mechanical shape of it. And so that's one of the ways that we're changing stiffness. But other people use things like materials that melt or re-solidify,
Mm.
or different granular and layer jamming to remove air and make something stiffer that way. So there's lots of really exciting ways to do this in soft robotics.
Yeah, I love the idea of using origami, like kind of blending old and new, like the ancient art of origami with the kind of the modern state of the art robotics technology.
Yeah, it's, I think, really interesting. And you say ancient, but there's lots of research in the last 10, 20 years about different patterns that give
Mm.
you these properties. So it's, I guess, this long and amazing history of origami and its properties.
Yeah, that's really cool.
So one of the things that I'm excited about with the origami project we're working on now is working towards making the origami actuators, the actuator part of the robot, strong enough to do lots of heavy lifting. So we have a demo recently where we held up a student in my lab using three of the origami actuators.
Wow.
And then we adjust the position of the actuator so it's a little bit of a balance board. And we have a demo where she rides the origami balance board.
That sounds amazing. I'll have to check that out. Um, so I guess eventually this could be used in kind of like an exoskeleton or kind of devices that provide like physical support to hold people's body weight.
Yeah, that's a lot of the things we're thinking are they may be integrated into devices that may hold or support a bit of someone's body weight, or really sort of similar structures already are used in the world that are passive. So things like the little shock absorbers in your shoes, if you
Mm.
wear trainers or gym shoes, that those are similar shape to what we do. And I think it would be really interesting to think about then making those devices active as well, increasing and decreasing the air pressure in those to get different properties as you're playing basketball versus running versus weightlifting.
Mm. Yeah, your shoes could have different settings for different activities.
Absolutely.
Amazing. How ready are these technologies to go out into the real world and be used by people?
I think it kind of depends on the application and what you want to do. So some of the devices that we're building in my lab, some of the soft sensors, we are getting ready for studies with participants. We're going to have lots of people come into the lab, and we're going to have them wear these sensors in a band and see what changes in sensor output we get as they do a bicep curl. They lift a heavy weight
Mm.
to see if we can recognize that motion and how that signal changes with time and across people. And I think that that is, that's one example of maybe 5 years from now, it could be out in the world. There are
Mm.
other soft sensors that are already on the market and are used in different ways, that have little electronics with them that you could buy one and go use it for your own purposes. And then there are some of the more far out things like the origami actuators that I think may never make it out into the world as a commercial product, but
Mhm.
are giving us a lot of really good information about soft robot behavior and control and approaches that really will let us build better soft robots in the future.
Mhm. Sure. And I mean, maybe this is not something that's they're quite at that stage yet. But what kind of regulatory steps or requirements are there for these kinds of devices? Because I've spoken to some like people who work, say, in surgical robotics, and the bar for getting new devices there is incredibly high. Obviously, I'm assuming if it's wearable, maybe the risks are a little bit lower, so perhaps the regulatory framework is slightly less strict.
So I think anytime you're talking about a device that can treat or diagnose a medical device, the regulatory bar is really high, as it
Hmm.
as it should be.
Yeah,
We want these devices to be safe for people.
absolutely.
Um, Wearable devices, I think, have a less high bar than implantables for thinking about biocompatibility.
Yeah.
But we do want to make sure that the information that we get from these sensors is really telling people what they need to know about their health.
Mm.
So I think it's really fascinating some of the existing wearables on the market that are not branded or promoted as wearable devices. People will say, "Oh, I wanted to do this. I wanted to do this. I wanted to measure my skin temperature every 10 seconds across the day." And there's nothing wrong with the device. It can certainly measure that data. But as soon as you do that, it is considered a medical device and has to go through all of these additional
Mm.
regulatory challenges. So I find it really interesting that even with some existing wearables, we're changing what the device can do, at least for the user, because we don't want it to be a medical device.
Right. Yeah, that's really interesting. I guess the obvious wearable that always springs to my mind is like the kind of step tracking watches or bands that you can wear. I guess that doesn't
Mhm.
quite cross that threshold of being a medical device.
Right. So it doesn't because it's giving you information about your life, but it's not giving you any necessarily medical recommendations. And if
Yeah.
you were to, for example, take your heart rate or heart rate variability and go talk with your doctor about it, that feels like a very different thing than the device saying, your heart rate is X, you need to go to the hospital right now.
Yeah. Yeah, definitely. So we had an audience question from Mary that was submitted on our website. So Mary says, "What is the biggest challenge in soft robots for healthcare?" So it's quite a big question.
That is quite a big question. I think there are a couple of different challenges that I think I would be remiss to not talk about maybe two of them. So, definitely power and how we actuate the devices is a big one. So,
Mm.
if someone has a medical device, they want that to be pretty seamless into their life. They pick it up, they put it on in the morning, and then they go. They don't want to worry about charging. They don't want to worry about lugging around a big air pump. Lots of soft robots right now use fluidic actuation or pneumatic actuation, changing air pressure in
Mm.
order to get the motions that we need. And somebody doesn't want to, have a purse size or backpack sized air pump that they have to carry around with them and all the batteries.
Yeah.
So that's a big one. And another big one is just figuring out how we make medical devices apply from person to person. So we know that one size doesn't fit all for most medical things.
Mm.
People need to hack them and tailor them and adjust and figure out how to make it work for them, or get guidelines from the device companies to make it work for them. And so I think another big question in soft robotics is how we tailor these devices so that we get the best performance for an individual, not just across an entire population.
Hmm. I guess compared to like more rigid robots, soft robotics kind of lends itself a bit more to tailoring.
Yeah, that's the nice thing. I think a lot of soft robotics are 3D printed or cast out of these soft materials. And so if I'm 3D printing a device for someone, I can take my CAD file, I can tweak it slightly and print another device for someone else.
Hmm. And coming back to the first challenge you mentioned of power, or the kind of the air pump, or these kinds of requirements. Do you have any ideas about how to approach that? Can are there advances being made in miniaturization, or I don't know, like solar power, or can we power things from the action of people walking?
So there are lots of different advances from other parts of engineering that I think soft roboticists are going to go, ooh, that looks great, and use it in our thing. So
Yeah.
you mentioned solar power. I had a paper last year where we studied where the best place to put flexible solar panels on the body if we want to power a wearable device.
Mm.
And so that turns out that, the stomach is a nice big area, but usually people might be sitting and blocking the solar panel. The shoulders, there's a lot of motion, so maybe not there. So we came up with this thinking about like little epaulets on the shoulder, little
Mm.
shoulder pads that don't see too much motion for these flexible solar panels. Another one is actually sort of pneumatic or air batteries that generate the pressure that these soft robots need to work without batteries themselves. And battery technology is getting so much better,
Hmm.
and it's easier to charge. They're getting more energy and power dense, and so I think that's another problem that other engineers are going to help us solve.
Sure. And so, thinking even more to the future, what is your vision for how this area of soft robotics is going to progress over the next 5 to 10 years?
I think the thing that would make soft robotics really a success story and really exciting is that it doesn't just be soft robotics anymore. It's this thinking or this particular performance of a soft robot gets integrated into bioengineering. And this other one gets fused a lot with rigid robots. And we're now just calling it a robot that happens to be soft.
Mm.
So right now, soft roboticists are really focused on solving a lot of the challenges of how we fabricate soft robots, how we control them, how we uh, do some of the same performance as rigid robots. But I think at some point, we're going to get to the point where soft robotics gets used in a lot of different fields. And that's where I'm really excited about it going.
Yeah, definitely. Yeah. I mean, when I first heard about soft robotics, it was like this totally sort of alien thing to me and presented very much as this distinct discipline, this separate area of robotics. But the more people I talk to, the more I see it being kind of integrated into more and more different areas. So that's really exciting.
Yeah.
And as these technologies develop further, how do you see them impacting healthcare and society more broadly?
So, I mean, one of the things I'm thinking about with soft robotics in healthcare generally is how do we make this a device that makes lots of people's lives better rather than the 10% of the world that can afford it?
Mm,
So I think one of the exciting things about soft robots is because they are or can be less expensive, that a lot of people are thinking about it as a more accessible solution for lots of medical and wearable challenges. But if we don't solve some of the key problems that make it so that we can put it in someone's hands that really needs it, then I think that we haven't served everyone that we could with these soft robots.
yeah.
So I don't have any good answers for you. I don't even quite know what the questions are, but it's something that I'm thinking about as a roboticist and something that I talk with my students a lot about.
Yeah, yeah, definitely. That's such an important point. Kris, it's been lovely talking to you today. I've been chatting to Kris Dorsey, an associate professor at Northeastern University. Thank you.
Thank you. It was a pleasure.
Thanks for listening. If you enjoy Robot Talk, please do share the podcast, subscribe, and leave a review to let us know what you think. And make sure you check out our social media channels to see a photo of the 3D printed soft origami robot that Kris and I talked about. We're at Robot Talk Pod on all the socials. Next week, I'm talking to Rolf Muller from Virginia Tech, all about biomimicry, flapping wing flight, sensing, and artificial intelligence. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.